x2h plus xy. I'll just write it as xy for now. And then over here you get another xy, and you get y2h. Right? Two factors where you decrease by h. That's the y times y minus h part right there. And so in between here, we happen to have 2 choose 1 times x to the 1h, y to the 1h. I know I didn't really need to rewrite all this. I just thought, why not start over? Why not waste some more ink? Yeah, so it's true for 2 as well, right? You're seeing that happen. This is the first time, and it's kind of interesting that you get a 2 there. So let's suppose we know for n minus 1 that we have this happening, that we have a formula for it that goes n choose k x to the n y to the k, like that, and this goes from 0 to n minus 1. So yeah, suppose we know that our formula is true for the n minus 1 case. We want to show that it's true for the n case. And I was like, of course, to get from here to there, we know what to do. We just multiply by this term, except it's not minus h this time, it's minus n minus 1h. So we know this is by definition. You just multiply this by x plus y minus, and this time we'll have n minus 1 h's, whereas this guy sort of contains n minus 2. That's the last factor that it has, is n minus 2 times h. But yeah, if you multiply this by this, you will get that. That's just the definition of this thing. And we know that this chunk here is given by this formula. So anyway, this is where we were on the other side of the sheet. This is where I had just stopped and said, I'm taking a break and I'm going to rewrite things. And I feel like you want to just use, you can exchange this with you can exchange this with this junk I was saying. You can use this identity. Pretty sure that's going to be the whole point. Like, that's going to be what makes this work. So I'm going to use the fact that, so let's see, I know this is true, same as this, and like, I also know that when you, like, I can, when this thing gets multiplied by x minus n minus 1h, it increases this exponent by 1. Same thing with the y. Well, hold up. Not exactly true with the y. You gotta be a little careful. But we can introduce a term here, I suppose, right? Yeah, it's not exactly true here because there's a k. So we're gonna need to split this up, like, can I do something like minus k plus k? Grrr. Yeah, you see what I was saying? Like, if k was 0, then part of what I was saying was true, but it's not 0, it's some integer. So you're going to want to, like, subtract kh and add kh, basically, inside this factor to make it happen. And my ADD is telling me I should just show you the answer because it's going to be much easier than what the hell I'm doing right now. But but let's not do that. So yeah, my brain is screaming at me to write minus kh plus kh in here to help start grouping things, but anyway, we can get this all on one page if I say recall that n choose k is the same as n minus 1 choose k plus n minus 1 choose k minus 1. So I believe we're going to replace this with this minus that. That's one thing that's going to happen. So one of them looks like, we're also going to have to drop, like, we're going to have to drop one of these terms, like, we'll remove the k equals 0 case in a minute. Yeah, I just want this to match up, right? What I was saying was, if it was n minus 1, I would have been very happy to have this here. So I want to make it look instead like n minus 1 minus k. And I can't just do that. I have to also add kh at the same time, you know? Oh, wait a minute. I'm subtracting this, right? So you're actually subtracting kh if you want it to look the same. Because here I added kh to make this happen. So add kh and subtract kh. This is one term. I also have minus this part. And I did this last week. I didn't do it on video. So like I know that this will eventually work out. But I obviously could have done it a little better. Like I'm not saying, this is definitely not the cleanest way to do it. If I had rehearsed this, I could probably do it in 10 minutes instead of whatever I'm doing here. So I haven't absorbed this in yet. This guy's still sitting here. And I just thought it would be helpful to change this. Because now at least like I can do some sort of grouping. I can say like x minus that combines with this to become x to the n minus 1. Not n minus 1, but like x to the n minus k. Okay? Which is closer to what we wanted, I guess. But yeah, very strange. Kind of gory details. Will we succeed? I don't know. Remember, of course, the goal is to make it look like this, but with n minus k. And then this index will also change. But that's about it. That's all we need to happen. Of course, I've got two terms right now, but two big sums. But I don't think I made a mistake, so that's maybe that's good. We'll see. I suppose this 0 term goes away. When you get to n minus 1, do you get n here? No, you get n minus 2. So it still makes sense. Huh. All right. So if I distribute this in, for each one of these terms that I used to have, now I have this guy increasing to x to the n minus k. You know, we added another factor of x minus thing times h. But then we also have, you know, plus this stuff times y minus, or sorry, y minus kh, which is good. Y minus kh will also affect this guy. It'll bump him up to be k plus 1. Oh, that's where the reindexing happens. Cool. But this one, it doesn't. No, it happens here too, right? It just becomes n minus k. Huh. Very confused for some reason. Maybe I did make a mistake somewhere. Anyway, you can sort of see what I'm driving at. Man, this is pretty ugly. It's funny, the other day I just stared at this for a minute and then I was like, oh, it's this, and I jotted down a line and it was easy. But that's what I get for not getting enough sleep today. I'm also potentially trying to do like too much in the same step here. Like, what am I going to do with this? I ultimately want this to be the one that survives. So apparently this stuff collapses into one term that kind of cancels out, or like this is the last term. This is that k equals n term. Dot dot dot. Yeah, I think this might be the only problem we do today. I'll try to get through the multinomial part too, but I was just going to try to read that. I wasn't going to try and do it myself. But I will finish this part, 36. So like at 0, you're getting yeah, I don't quite see it. Do some terms cancel or something? I'm not seeing it. Anyway, and was this a horrible idea? Maybe I should have left that alone. Like, maybe this was throwing me off. It certainly made it look worse. I should have waited until that was relevant, you know? We can go back if you want. Let's go back for a sec. But anyway, this guy's, we're going to do this trick. We pull them in. So let's just say or, because I'm undoing this trick for some damn reason. I think we do want that though. I think we do want that. I just don't quite. So like this guy times this term. Let's do it this way. I won't do anything yet. I'll just say it's this times x minus n minus 1 minus k h, right? And then we've also got I'll add it. I don't really know if this is right. But yeah, we're multiplying also by y minus kh. Anyway, the reason I did that is that we know this groups, and we know that this guy groups with that. So there's a cleaner way to write this stuff. As x to the, I suppose it's n minus k, and then there's an another sum here, where this stays the way it was, but the y gets incremented to k plus 1. All right, so that's one thing that happens. Now that's kind of like this grouping that I saw in the easy case, right? In the case of going from 1 to 2. I don't remember this being very difficult the other day. It's too bad I threw out my notes, huh? Yeah, I don't think this is not that hard. I don't know why I'm just staring at it. Isn't this almost what you wanted? Almost. Okay, well, I've got to be able to just like change this and re-index, but it's never gonna. I mean, what happens if you just re-index right now? So there's a 0 term that is still going to be there, and there's an n minus 1 term that is also still going to be there. Huh. Alright, fine. But I just kind of wish it looked like that, right? So I almost want to get rid of this first term and see what happens. But then when I re-index, I lose this term. It feels like I'm going the wrong direction. Like, shouldn't I have an nth term? I'm starting to see why he didn't do it this way. I could show you what he did, by the way. Where is it? 36. Oh, cute. He just says, look at 35. Hold on a second. 35 is the one I'm working on. Okay. Cute. I don't know how I'm going to make any sense of the multinomial case. Is that what that is? Yeah, 36 is just prove the following. But anyway, his answer for 35 is like 2 lines, right? This is trivial. He makes this observation and then he doesn't do it my way, but I think I'm still going to see if my way works out. My way is pretty easy when you know what to do, but for some reason I'm just staring at it. But no, he says, for some reason this happens, which obviously I hadn't noticed that. Oh, okay, sure. So, wait, where's the h to the n come from? Oh, because he divided. Yeah, I still don't quite see it, but it must be kind of obvious. The n factorial part is obvious, like he introduced that. Otherwise, that is almost the exact definition. So yeah, I could sort of see it being true. But then because of that, if you divide, sure, you just get this part. And he's saying that's the same. Oh yeah, it is 1 plus hz. So he's just using the binomial theorem. I see. Cute. Wow, that is really slick. But it all kind of hinges on this part being true. Wow, this is a lot easier and faster than what I'm doing. So he notices this relation and then throws it into the binomial theorem, and that's about it. And boom, that's why binomial theorem is still true. For 36, is this maybe like I just need to be more familiar with the multinomial theorem to begin with? Because 36 he has no answer. He basically just says, yeah, look at 35. So it's clear that he's just like saying, you know, this is what you would have in the regular binomial theorem case, so you still have it here in this case. So that's 35 and 36 if you wanted to be completely done with this problem. It all just hinges on like this was the definition. And you can see another, well, I guess he divided by h. That's how he was able to start writing it as factorials. Like, if you instead looked at x over h times x over h minus 1 times x over h minus n minus 1, then other than the fact that you had to divide by a bunch of h's, so this is the same as having n factors of h factored out of your denominator, you know. But then the reason he probably did that is that now this is just regular old factorial. So this is h to the n times x over h factorial divided by, it looks like x over h minus, it's got to be n, right? Like that is a cleaner way of writing this finite set of factors. Yeah, n minus 2, n minus 1, n. So n is the one that gets canceled along with everything smaller than that. Minus n plus 1, minus n plus 2, etc. So that's how you write that. And then he's observing that if we, you know, multiply and divide by n factorial, then you're looking at x over h, choose n, I suppose. Sure. And then I forget where he went from there, but I remember it. He was expanding this just using binomial theorem, right? This formula that you were talking about expanding is this. Anyway, this would give you sum of n choose k, hz to the k. This k goes from 0 to n. Oh, I know what he's doing. He's probably looking at, he says take this series and divide by n factorial. Like, he's looking at, I was going to say he's putting it here in like a, yeah, I'm trailing off here because I forget his next line, but he obviously expanded this. We were looking for a formula for this, which is this. So he put it inside of a, fine, I'll just look again. He treated it like, yeah, exactly, like a power series with a factorial in the bottom, like a power series, like a Taylor series, for instance. He was using this jazz again, you know. Anywho, so when you do that, of course, the n factorials cancel, and you get just this part. Like, yeah, there's a Zn there. I was like, why do I want to write Zn? Probably because it's there. But this part would cancel and give you the sum of just like x over h, choose n, times h to the n, z to the n. Which, I mean, I could see how we got this. I'm just a little fuzzy on. Oh, right. Right. Cool. Good. That's what I was going to say. All right, good. I was going to say, well, then we need n to be x over h, but that's fine. Because it doesn't have to be like an integer. That's always my hang up. Man, I'm so sick of that. I always see like, you know, obviously this can be a real number, but you know, I see like the binomial theorem and I'm always like, oh, make sure that's like a positive integer. But I don't know why I keep worrying about that. It's never an issue. So yeah, this looks an awful lot like the binomial theorem, except that this is not an integer, but who cares? So this would be 1 plus hz to the power x over h is what you'd be looking at. Why do I care about that? Why is that good? Well, we were trying to get a formula